On the 7th of January 2016, the National Aeronautics and Space Administration established the Planetary Defense Coordination Office. Built on the foundation of NASA's older Near-Earth Objects Observations program, this new organization is intended to continue funding and coordinating ongoing search and research efforts for near-Earth objects, generally shorthanded as NEOs, identify strategies to reduce the risk of future large impacts by NEOs, called mitigation, and coordinate emergency response actions with other federal agencies and international partners. The new office's initial budget was set at $40 million per year, up from about $4 million in 2010. A number of highly public recent events preceded this action. Most prominently, an object about 20 meters in diameter impacted Earth's atmosphere and exploded at an altitude of about 23 kilometers near the Russian city of Chelyabinsk on the 15th of February 2013, releasing the energy equivalent of about 500 kilotons of TNT. The explosion was high enough above the surface that it did only modest structural damage, but even so, there were over 1,500 injuries, mostly from glass shattered by the violent shockwave initiated in the blast. By chance, the fireball was recorded on dashboard cameras installed by Russian citizens to record accidents and police encounters, resulting in an unprecedented circumstance. Unlike every other known NEO impact, the Chelyabinsk airburst was a visual event that could be widely shared and broadcast worldwide. The Chelyabinsk event was the largest NEO airblast since the Russian Tunguska event of 1908. The energy of that explosion, though poorly recorded due to the location's remoteness in a Siberian forest and the lack of communications technologies, is gauged to have been about an order of magnitude greater than Chelyabinsk's. Estimated to have been around 40 meters in diameter, the Tunguska impactor flattened about 2,200 square kilometers of forest. For comparison, the largest recorded California wildfire as of September 2021, ignited by lightning and known as the August Complex Fire of August 2020, burned nearly 4,200 square kilometers. These extraterrestrial visitations have always happened. Earth experiences annual meteor showers of objects that are nearly always too small to reach the surface. These clouds of near-Earth objects have names. The Perseids occur in August, while the Geminids occur in December. They are the result of Earth's passage through the debris trails of comets or asteroids, with the Perseids, for example, originating with Comet Swift-Tuttle and the Geminids with asteroid 3200 Phaethon. And there are other such showers, too. Ancient civilizations knew of them, though they generally interpreted them as signs from their gods, and not as we do, as relics of the solar system formation process. Interestingly, for most of human history, these apparitions were often imbued with malign intent. They were, in other words, seen as portending ill. The classical astronomer who probably did the most to categorize the variety of damage foretold by comet appearances was Claudius Ptolemaeus, usually called Ptolemy. Ptolemy is mostly known for his Almagest, the treatise in which he developed the theory of epicycles to describe the motions of the heavenly bodies. In Ptolemy's cosmology, the heavens rotated around a spot slightly off-center from a stationary Earth. Although incorrect, Ptolemy's theory predicted the motion of the known planets and stars quite accurately, well within the measurement capabilities of astronomers for another 16 centuries. Because of this, Ptolemy remained a central authority in astronomy until the Renaissance. Ptolemy's Almagest did not include comets, because he, like the influential Greek philosopher Aristotle before him, did not consider them heavenly bodies. Aristotle had considered them emanations arising from Earth itself, while Ptolemy only mentioned comets once in his astrological work, the Tetrabiblos. In this work, he described in some detail how one could read the omen represented by a comet's apparition. Its position with respect to the sun indicated the timing of the coming disaster, while its tail noted the location. The shape of the comet was supposed to foretell the nature of the disaster. The Tetrabiblos was just as influential as the Almagest, though in a different way. It was embedded in Catholic theology during the many centuries of the European Middle Ages. If classical astronomy can be seen as an effort to understand and predict the motions of heavenly bodies, classical astrology can be interpreted as astronomers' efforts to predict the influence of those bodies on humans and on human events. Ptolemy was not alone in practicing astronomy and astrology simultaneously, though he placed them in different books. Most astronomers prior to the modern era made their livings as astrologers. Society's wealthier members were much more interested in predictions relevant to everyday life than they were in the mere motion of the heavens. This was equally true in ancient China, where court astronomers had been making detailed observations of the heavens and of comets for centuries before the Almagest in order to provide astrological advice to their rulers. Finally, it is important to note that while pre-modern civilizations saw comets as omens of ill fortune, they did not see comets as the cause of that ill fortune. Fickle or vengeful, gods and goddesses were the actual agents of destruction. Comets were merely warnings. The Almagest's influence gradually broke down among Western astronomers during the 17th century, rooted as it was in the failing notion of geocentrism. It is less clear that the influence of the Tetrabiblos ever did fade completely, although it is no longer part of Christian doctrine. Comet apparitions of 1607 and 1618 once more sparked debate among astronomers over their nature. The 1618 comet was the first to be observed with a telescope, and astronomers began to understand them as physical objects rather than as omens sent by deities. But comets were also not quite fully accepted as permanent features of the cosmos. Johannes Kepler, who in this era demonstrated that planetary orbits were calculable as ellipses, believed comets were ephemeral and moved in straight lines. Other period astronomers believed them eternal, moving in orbits, though not necessarily centered on the sun. Edmund Halley's 1705 treatise on comets began to solidify an elite opinion around the idea that at least some comets were repeat visitors. Using a technique developed by Isaac Newton, he computed orbits for 24 comets that had appeared between 1337 and 1698, and he contended that a single comet actually accounted for 3 of those visits. It had appeared in 1531, 1607, and 1682. He also predicted its return in late 1758 or early 1759. Though Halley did not live to see his comet's next reappearance, it did return. A German amateur made the first recorded observation on Christmas evening, 1758. Halley's comet, as we now name it, settled the question about cometary longevity and rendered these objects relatively predictable members of the cosmos. If one could track a comet for the few days or weeks of an apparition, one could generate its orbital characteristics and predict its future motion. Halley also had the foresight to wonder what would happen should a comet strike Earth. But he did not strongly pursue the question, perhaps wisely for the sake of his reputation. The same century in which Halley's comet prediction was made and confirmed also witnessed the development of the doctrine of uniformitarianism within the natural sciences. Uniformitarianism taught, in various formulations, that the present is the key to the past. It was articulated in 1795 by James Hutton and subsequently popularized and purged of its religious overtones by John Playfair's 1802 revival. Illustrations of the Huttonian theory of the earth. Uniformitarianism proposed that the same natural laws and processes operating today have always operated throughout Earth's history at the same rate and across the entire planet. Hutton's uniformitarianism was adopted by Charles Lyell, whose Principles of Geology, published between 1830 and 1833, established it as a central tenet of geological thinking in the 19th century. In a prior statement, Hutton illustrated the distasteful connotation attached to the catastrophist side, rejecting appeals to any destructive accident in nature or to the agency of preternatural cause in explaining what actually appears. For both Hutton and Lyell, changes on Earth like the gradual cycles of erosion or uplift occurred over an inconceivably vast time span, providing no hope of deducing either a beginning or an end. Intended to remove natural science from theology, for example, the biblical flood would be catastrophic and thus unacceptable as an explanation under uniformitarian ideals. It also led scientists to reject natural cataclysms as an explanation for Earth's features. Extraterrestrial impacts could not be shapers of Earth. Thus, one interesting effect of uniformitarianism on the Earth sciences was the separation of Earth from its cosmos. Only the sun and moon were permitted to have influence on Earth. By the end of the 19th century, Not only were comets no longer widely seen as omens of ill events, they were no longer seen as relevant to human or earthly affairs at all. Comets were but one type of occasional celestial visitor. Meteors, and the mysterious remnants they occasionally left behind, were another. Reports of meteorite falls date back nearly as far as the dawn of written history, with accounts preserved in ancient Egyptian, Chinese, Greek, and Roman literature. Myths and religious writings record still more ancient events, such as a set of traditions related to the Campo del Cielo fall in northern Argentina 4,000–5,000 years ago, the Bible passage referring to the Temple of Artemis in Ephesus as the image that fell down from Jupiter, the Phoenician legend of Astarte bringing a star fallen from the sky to the island of Tyre to be worshipped, and the disputed meteoric origin of the black stone of the Kaaba in Mecca. Tools and items of religious significance made of meteoric iron have also been discovered at many archaeological sites. The oldest known worked iron artifacts are a collection of Egyptian beads dated to 3200 BC made of hammered and rolled meteoric iron, and the extraterrestrial signature of a knife taken from the tomb of King Tutankhamun in 1925 has recently been confirmed by chemical analysis. Many Native American artifacts have been discovered at burial sites across North America, and several Chinese Bronze Age axe heads containing meteoric iron blades have been documented. Despite these widespread accounts and the demonstrated influence of meteorite falls on cultural myths and traditions, they were not generally accepted as rocks from space until well into the 19th century. The absence of known source bodies, pressure to find explanations in known terrestrial phenomena, and skepticism of eyewitness accounts all played a role in fostering doubts as to the extraterrestrial origin of meteorites. In the 1700s, the conception of the divinely maintained clockwork solar system established by Isaac Newton was no place for stray objects. Even when observations of comets and stellar novae established that the universe does indeed change over time, the existence of cosmic debris remained difficult to accept. This long insistence on an empty universe, as well as the tinge of superstition attached to reports of falls and fireballs, fueled attempts to find explanations for these phenomena in more familiar terrestrial experiences. One such explanation involved the condensation, often in conjunction with a lightning strike, of minerals within the atmosphere. This idea, bolstered by contemporary enthusiasm for recently discovered electrical phenomena, retained support well into the 19th century. By that time, however, chemical analyses had revealed that the majority of fallen and found stones are both remarkably similar to each other in texture and composition, and markedly distinct from the typical rocks of Earth. This observation pointed to a single external origin for meteorites, and the Moon was an obvious candidate. Fanned by several dramatic eruptions of Vesuvius and Etna starting in the 1760s and followed by alleged observations of lunar eruptions, support for a lunar origin for meteorites persisted into the middle of the 19th century, eventually to be defeated by dynamical considerations. While the atmospheric and lunar volcanism theories for the origin of meteorites declined, a cosmic origin seemed increasingly possible. In the 1790s, Ernst Florenz Friedrich Chladni drew an explicit and unprecedented connection between meteors, fireballs, and native irons, proposing an extraterrestrial origin for these three phenomena, previously considered distinct. He proposed that meteorites were fragments of matter that either had never consolidated into a planet or had emerged from the violent disruption of a planet by a collision or internal explosion of some kind. Chladni's first report was followed over the next several years by an entirely coincidental spate of highly prominent falls, culminating in the spectacular fall of thousands of stones at L'Aigle, France, in 1803. The widespread publication of these events, including a comprehensive report on the L'Aigle Fall, completed by Jean-Baptiste Biot on behalf of France's Minister of the Interior, did much to establish that rocks do indeed sometimes fall from the sky. The discovery of Ceres in 1801 provided a new hypothesis for the origins of these rocks, although other, more local explanations retained their currency until about 1860. While conducting observations for what would become a famous star catalogue, Italian astronomer Giuseppe Piazzi discovered a new object, Ceres, in an orbit that appeared more planet-like than comet-like. Ceres also fit what is known as the Titius-Bode law. Published in 1766, this rule inferred from the spacing of the inner planets that there should be a planet between Mars and Jupiter, another beyond Saturn. The 1781 discovery of Uranus, approximately where the Titius-Bode law had forecast, seemed a confirmation of its accuracy. Ceres, too, was in the right place. Piazzi first thought it might be a comet, but other astronomers doubted that. After the 1802 discovery of Pallas, traveling in a similar orbit, William Herschel declared the two objects to be a new class of celestial body, asteroids. The asteroids occupying orbital space between Mars and Jupiter are known collectively today as main-belt asteroids, to mark a distinction between them and the many other varieties of asteroid orbits discovered since. They are still the largest known asteroid population, and one, Ceres itself, was later reclassified as a dwarf planet by vote of the International Astronomical Union in 2006. Main-belt asteroids' orbits generally keep them far away from Earth, and they are not classed as near-Earth objects. But their orbits can be perturbed, and over the eons some have been shifted into orbits that take them into the inner solar system. The first such near-Earth asteroid to be discovered was 433 Eros, found in 1898 by German astronomer Gustav Witt. Since the discovery of Eros, scientists, and many devoted amateur astronomers, have identified many thousands of near-Earth asteroids, but far from the uniformitarian view that extraterrestrial impacts could have no influence on Earth. A very large impact is now blamed for the demise of the dinosaurs, and numerous craters associated with large extraterrestrial impacts have been identified on or under Earth's surface. These impact craters are known as astroblems, bringing the geological community around to the idea that asteroids and comets have, in fact, left marks on Earth's surface, was the life's work of Eugene Shoemaker, who also trained the Apollo astronauts in field geology, and whose wife, Carolyn, was one of the most prolific discoverers of comets during the era when film was the discovery medium. The recognition that large impacts could influence the evolution of life itself is an extension of what is known as the Alvarez hypothesis, named for a famous 1980 paper by Luis and Walter Alvarez. This posits that an impact at the end of the Cretaceous period forced the dinosaurs into extinction. Acceptance of the idea that large impacts have transformed both the surface of Earth and life itself represents a rejection of strict uniformitarianism, or what Stephen Gould referred to as substantive uniformitarianism in a 1965 essay. Three events in close succession brought the potential destructiveness of cosmic impacts to public attention and began moving NEOs into policy salience. The first was the unexpected close flyby of Earth by 1989 FC, discovered after it had already passed by. The discovery of the enormous buried crater left by the end Cretaceous impactor in 1990 was the second. The spectacular collision of comet Shoemaker-Levy 9 with Jupiter in July 1994, witnessed by ground observatories, the Hubble Space Telescope, and the Galileo spacecraft en route to Jupiter, was the third and most dramatic event. These led to the Congress directing NASA to find at least 90% of the 1-kilometer diameter or larger near-Earth asteroids within 10 years. And NASA currently has a directive to discover and track 90% of all the near-Earth asteroids larger than 140 meters, those about 7 times the size of the Chelyabinsk impactor, which could cause regional damage on Earth in the event of an impact. Once near-Earth objects became objects of policy concern, they also became hazards to be mitigated. The discovery of NEOs and the determination of their trajectories was one component of mitigation, but as policy measures started being discussed, other aspects emerged. Deflecting specific threats was one recurrent theme of discussion. Another was civil defense. The first decade of the 21st century witnessed the first impact-related civil defense exercises in the United States, and both NASA and the European Space Agency had plans for deflection demonstration missions to be carried out in the 2020s. At the international level, advocates of planetary defense had established an international asteroid warning network to coordinate observations as well as communications about particular asteroid risks, along with a separate planning group for space-based deflection missions should one be necessary. This also reflects the gradual internationalization of NEO concerns. In a recent article, Valerie Olson argued that asteroids and comets have come to be seen as environmental objects, as distinct from astronomical ones. They are no longer merely intellectual curiosities or research objects for scientists. They are natural hazards like flooding or wildfires and are increasingly treated as risks subject to cost-benefit analysis. Astronomers use this tool of the administrative state as part of their advocacy for NEO discovery surveys and planetary defense efforts. Most near-Earth asteroid discoveries have happened since 1990. In large part, that is due to a technological change in the way astronomers look for them. For most of the 20th century, astronomers interested in near-Earth objects, there were not many, had to compare two pieces of film taken of the same piece of sky, but at different times, to find whatever had moved between exposures. It was a painstaking, slow process. During the 1970s, though, Jet Propulsion Laboratory researchers worked to improve charge-coupled detector technology, we call them CCD, for eventual use in spaceborne cameras. A prototype CCD-based camera was used by James Westphal and James Gunn at Palomar Observatory in 1976. By 1981, the University of Arizona astronomer Tom Garrels was trying to fund a CCD-based telescope dedicated to hunting near-Earth objects at Kitt Peak Observatory. Failing to raise enough money, he and a small team developed the Spacewatch camera, which was attached to an existing 0.9-meter telescope to produce its first electronic images late in 1983. CCDs lent themselves easily to computer-assisted analysis, and by the mid-1990s, other teams were also striving to automate the process of NEO discovery, orbit determinations, and risk-to-Earth assessments. By the 2000s, hundreds of near-Earth objects were being discovered per year with the aid of automation, and right now, we're at about 25,000 and counting. We were kind of far from the truth, don't you think? I mean, if we got from godly signs to taking photos of NEOs in 300 years, imagine what we can do in the next 300 years, if we get there. By the looks of it, technology is slowing down, at least in our field, and we are more interested in finding planets and asteroids that contain valuable resources, especially rare and expensive minerals. Well, at least it's something. You do need technology to mine those off a moving asteroid in space, so I guess we are going in the right direction, but for the wrong reasons. But hey, the best inventions were accidental, so keep your fingers crossed on this one, for it might bring answers to the origin of the universe itself. Unless we find a way to mess things up, as we always do.